Dear students, I welcome you for the today's lecture where we are going to discuss the numericals associated with the Bode plot. We have already studied the procedure for plotting the Bode plot. This is a frequency response technique in which we have already discussed for the first order, second order, then the different controllers. Now today we are going to discuss the numericals. While plotting the Bode plot, we are having the two things, that is one plot is related to the amplitude ratio against the radian frequency, and second plot that is related to the phase angle against the frequency. So in case of a proportional controller where the transfer function is Kc, we are converting it into the complex number and rationalizing it. So amplitude ratio, that comes as the Kc, and phase angle, which is equal to tan inverse of 0 upon Kc, that is 0. So similarly here the plot of amplitude ratio against the radian frequency, it becomes a straight line passing through the 1, because the amplitude ratio upon Kc, its value, that is 1. And phase angle against radian frequency, that is the angle with a 0 degrees. The next is our PD controller, in which the transfer function of PD controller Gs, which is equal to Kc into bracket 1 plus tau ds. We are writing it into the complex number and separating the real part and the imaginary part, taking the amplitude ratio, which is equal to under root of real part square plus imaginary part square, and the phase angle, which is equal to the imaginary part upon the real part. So this is the amplitude ratio that comes as Kc square plus Kc omega tau d whole square, and phase angle, that is tan inverse of omega tau d. So for plotting this, we are calculating the low frequency asymptote where omega, that tends to 0. It is not actually 0, but it tends to 0. So it will have the very low values. So omega tau d, this is what the omega tau d that will be there, that also tends to 0. That means AR upon Kc, that will be equals to the 1. So log of AR upon Kc, which is equal to 0. So as the amplitude ratio, which is equal to 1, when it is plotted on the logarithmic plot, it becomes a straight line passing through the 1. And that is why AR upon Kc, it's a straight line that is passing through the 1. This is low frequency asymptote. Now what happens to the high frequency asymptote? That means the omega is having the higher values. That means it is tending towards the infinity. So omega tau d, that tends also towards the infinity. That means a very high values. So for amplitude ratio upon Kc, which is equal to omega tau d, so this becomes 1 is negligible, and omega tau d under root है तो square करने के बाद में that becomes your omega tau d value that will be there. So knowing this amplitude ratio, what is there, and knowing the theta, we have to substitute the 0 value and we have to substitute the infinity values and calculate the value of AR upon Kc, and then plot that value on the log graph paper. So it's a log of AR upon Kc, that becomes equal to the log of W tau d. So this is the point of this is the line passing through AR upon Kc, which is equal to the 1. So W tau d, that is having the slope of plus 1. So high frequency asymptote will have the slope of plus 1, where plus 1, that is 1, and 100, that is there. Similarly here 1 and 100, then and only then it will have the slope of +1. Next is the point of intersection of the low frequency asymptote and high frequency asymptote is known as the corner frequency, which is 1 upon tau d, or nothing but W dash is the corner frequency, which is 1 upon tau d. So this is the 1 upon tau d is the corner frequency. Next is the phase angle. Phase angle, which is theta, which is equal to the imaginary part upon real part, that comes as the W tau d. So substituting the values of W tau d as 0, theta that becomes equal to 0, W tau d that is equal to 0.01, phase angle you can calculate the theta, which is equal to tan inverse of 0.01. That gives you the value of 0.572. Similarly, you can calculate for 0.1, 1, 10, 100 and infinity, and then plot a graph. So for the value of 1, it comes as the 45. For the value of W tau d, which is equal to 1, the phase angle is minus 45. So this is what the minus 45 is, the phase angle. Then next is the proportional integral controller, GS, which is equal to the Kc into bracket 1 plus 1 upon tau Is. So substituting or converting it into the complex number, substituting S is equal to the j omega and separating it into the real part and the imaginary part. So amplitude ratio is nothing but under root of real part square plus imaginary part square. The real part is what is Kc. So Kc square plus imaginary part square, that is the Kc upon omega tau I. That is what Kc upon omega tau I whole square. So it comes as Kc under root of 1 plus 1 upon omega tau I whole square. Similarly, the theta phase angle, which is nothing but the imaginary part upon the real part. So imaginary part kk will get cancelled, 1 upon W tau I, that will be there. Now plotting the Bode plot, we will consider our formula is amplitude ratio, which is equal to 1 plus 1 upon omega tau I whole square. So considering this formula, when W tends towards the 0, that is WTI will also tends towards the 0. So amplitude ratio upon Kc, that becomes equals to the 1 upon W tau I. So log of amplitude ratio upon Kc, which is equal to minus log of WTI. So this is the equation of line passing through amplitude ratio upon Kc, which is equal to 1, and WTI, which is equal to 1. So this is y is equal to mx plus c. C is 0 there, and m is the slope, which is having the minus 1, and WTI is nothing but our x-axis. So similarly, high frequency asymptote where omega tends towards infinity, so 1 upon WTI, W tau I tends towards the 0. So amplitude ratio, that comes as 0. So it's a line of amplitude ratio upon Kc, which is having the 0.1 value. So similarly, WTI, which is equal to 0, that is nothing but the phase angle, that comes as the minus 90. So our formula of theta, which is equal to tan inverse of 1 upon W tau I. So substituting 1 upon W tau I as 0, 1 upon infinity, that becomes equals to the theta is minus 90. So similarly, by substituting 1 and substituting infinity, you will get the 3 values. Then we will plot a graph which is having the values of minus 90, minus 45 and 0 for 0, 1 and infinity. For 0, 1 and infinity, this is what the 1 that is there, and 0 to minus 90 its values are. The next is your PID controller. The transfer function of a PID controller, which is nothing but Kc into bracket 1 plus tau ds plus 1 upon tau is, converting it into the complex number by substituting s, which is equal to j omega, separating the real part and the imaginary part, that is 1 plus j into bracket w tau d minus 1 upon w tau I. So the amplitude ratio upon Kc, the real part square plus imaginary part square, and theta, which is equal to the imaginary part upon the real part. So you will get the amplitude ratio as 1 plus omega tau d minus 1 upon omega tau I whole square, and theta, which is equal to tan inverse of omega tau d minus 1 upon omega tau I. Now here the low frequency asymptote and high frequency asymptotes, they are to be calculated, that we will see in the numerical with a certain specific values. Now this is the same problem related to the proportional integral and derivative controller. So this is the time constants they have been provided. This is what the problem that is provided, 1 plus tau ds plus 1 upon omega tau I. So tau d is having the given value of 0.04 minutes and tau I, which is equal to 1.6 minutes. So substituting these two values in the given numerical of proportional integral and derivative controller, you will get 1 plus 0.4s plus 1 upon 1.6s. Then by substituting j s, which is equal to j omega, that means we are converting it into the complex number, and then separating the integral real part and the imaginary part, writing the amplitude ratio, which is equal to under root of real part square plus imaginary part square. So that comes as root of 1 plus omega tau d minus 1 upon omega tau I. This is the same as what is represented here by substituting the all j omega, that is 1 plus omega tau d minus 1 upon omega tau I. So this is the same thing. In this numerical, tau d value is given and tau I value that is also given. So similarly, theta, which is equal to tan inverse of omega tau d minus 1 upon omega tau I. Now we have to plot the Bode plot. So this is the first omega tends to 0, and that means omega tau d, our formula of amplitude ratio upon Kc, which is equal to 1 plus omega tau d minus 1 upon omega tau I whole square. So substituting these values, we are having the two asymptotes now. One is related to the derivative and another is related to the integral part. So it's a combination of a derivative and the integral, both the actions. So in this derivative action, the slope is plus 1. You can see this, the tau d plot we have already discussed. The slope is plus 1 in this derivative, and the low frequency asymptote is with a 1 value. So similarly, in case of an integral action, our graph, that is slope is minus 1. Integral action, the slope is minus 1 and amplitude ratio upon Kc, that is having a value of 1. So it's a combination of both the things now. So W tau d, when substituted to the 0, this becomes 0, and amplitude ratio upon Kc, that will correspond to the 1 upon omega tau I. So this is log of amplitude ratio upon Kc, that becomes equal to the minus log of omega tau I. So this is the equation of line passing through amplitude ratio, which is equal to the 1, and omega tau I, which is equal to 1, having the slope that is minus 1. So we will plot a line with a slope of minus 1. This is a line with a slope of minus 1. The next is the high frequency asymptote, and the next is high frequency asymptote, that is omega tends towards infinity, omega tau d tends towards infinity, and this omega 1 upon omega tau I, that will tends towards 0. So it will depend on omega tau d. So log of AR upon Kc, which is equal to log of omega tau d. So this is the equation of line passing through omega tau d, which is equal to the 1 with a positive slope. So this is the positive slope which will be there. Now where these lines are to be plotted, that also we will see. The corner frequencies of most importance in this case. So corner frequency is nothing but the point of intersection of low frequency asymptote and the high frequency asymptote. So low frequency omega 1, that is the corner frequency, first corner frequency, which is 1 upon tau I. So tau I value, that is nothing but 1.6. So omega 1, which comes at 0.625, and similarly the corner frequency omega 2, that is 1 upon tau d, that will be there, which is equal to 1 upon 0.4, that comes as 2.5. So 0.625 and 2.5, these are the two corner frequency points. So 0.625 and 2.5, these are the 2 points where the corner frequency is there. That is low frequency asymptote and the high frequency asymptote, they will intersect at that point. So this is the corner frequency, first corner frequency with the integral time, and with the derivative time, the second frequency, corner frequency, that is omega 2, which is equal to 2.5, that will exist. So one is because of the integral time constant, and second, that is because of the derivative time constant. So that will depend on the time constant values. The next is the phase angle. Phase angle for low frequency asymptote, omega tends towards 0, omega tau I, that tends towards the 0. So 1 upon omega tau I, that is infinity. So phase angle is minus infinity, that will be there. And in case of high frequency asymptote, omega tends towards the infinity, omega tau I tends towards the infinity. So because look at this basic formula, you have to substitute this omega that tends towards the infinity values. So omega tau d, this value will be neglected. So omega tau d, that tends towards the infinity. So it will depend on omega tau d. So 1 upon omega tau d, which is equal to the 0. This is the phase angle that comes as the 90. So it is minus 90 to plus 90. That will be variation for this omega. Now the next example we will see, it's a combination of two first order systems. We are having, or we are knowing the first order systems, its transfer function, that is nothing but 1 upon 1 plus tau s. So this example of GS, which is equal to Kc upon 0.1 s plus 1, and the second is s plus 1. So there are two first order systems. So we are going to separate these two first order systems, and we are making the G1s, that is the transfer function of the one system, and the second, that is the GS2, the transfer function of the second system. So one by one we will draw the low frequency asymptote for individual system, and then we have to club both the systems. So one by one, first we will see the transfer function for 0.1 s plus 1, this transfer function. So amplitude ratio, which is equal to 1 upon under root of 1 plus 0.1 omega square. That is what is our amplitude ratio, that is nothing but 1 upon under root of 1 plus omega tau whole square. That is what is the first order system. Transfer function amplitude ratio for first order system. Amplitude ratio for first order system, that is nothing but 1 upon under root of 1 plus omega tau whole square. You have to remember this thing, and this will be applicable for every first order system equations. So the same thing I am going to write it here as amplitude ratio, which is equal to 1 upon root of 1 plus 0.1 omega whole square. In this case, tau, that comes as the 0.1, tau s, that is what is the 0.1 s, that will be there. So 0.1 omega, the whole square, that is there. So I am writing 0.1 omega into 0.1 omega. Now the low frequency asymptote where omega tends towards the 0. Now if omega tends towards the 0, so this value will become tends to the 0. So it will depend only on 1. So amplitude ratio, that comes as the 1. So this is the equation of line passing through the amplitude AR upon Kc, which is equal to 1. So this will be the line for the low frequency asymptote. Now for the high frequency asymptote, that means omega tends towards the infinity. What will happen? So I am going to substitute the omega value towards the infinity. So it becomes 0.1 omega, अंडर रूट निकाल लिया है, ये स्क्वायर टर्म है, so it becomes 1 upon 0.1 omega. So log of amplitude ratio, which is equal to minus log of 0.1 omega, that will be there. So this is the equation of line passing through amplitude ratio, which is equal to 1 and 0.1 omega, and with a slope of minus 1, with a slope of minus 1. So this is the line with a slope of minus 1. This will be the line with a slope of minus 1. And where the corner frequency is 0.1 omega, which is equal to the 1. Amplitude ratio, that comes as the 1. So 0.1 omega, that is equals to the 1. So omega you can calculate as 10. So 10 will be the my corner frequency for this first transfer function, that is G1s with a slope of minus 1. Now next is for the second function, second transfer function. This is what we have discussed for this thing. Now we will discuss for the second transfer function. So G2S that comes as 1 upon S plus 1, and so 1 upon under root of 1 plus omega square. So again the low frequency asymptote omega tends towards 0. So amplitude ratio omega tends towards 0. So amplitude ratio that comes as the 1. So I am again plotting the amplitude ratio that comes as the 1. That means this is the equation of line passing through amplitude ratio is equal to the 1. Then for high frequency asymptote omega tends towards infinity. Now I am going to substitute omega tends to higher values. So it becomes 1 upon omega. So this equation that will becomes equals to the 1 upon omega. So this comes as the 1 upon omega. So amplitude ratio 2 that comes as minus log of omega. So it's a line with a slope of minus 1. So I am going to plot a line again with a slope of minus 1. But the corner frequency, that is omega 2, the point of intersection of low frequency asymptote and the high frequency asymptote is the corner frequency. So omega that comes as the 1 in this case, amplitude ratio 2 which is equals to the 1, this is nothing but omega 2 that comes as the 1, and in the first case the omega that is corner frequency that comes as the 10. So now combining both these two, the transfer function for this second is slope with a minus 1 and the transfer function with a slope of minus 1. So combining these two, you will get the slope of minus 2. Slope of minus 1 plus slope of minus 1, that becomes equal to the slope of minus 2. This is what the resultant resultant overall slope that will be there. So it's a overall slope of minus 2 that will be there, because with a one transfer function this is the minus 1 slope, with another transfer function this is the slope. So for this omega 2 that comes as the one corner frequency. So this is my one corner frequency. However, for the previous, that is GS1, that is the corner frequency as 10 is there. So it is going to change the corner frequency by addition of the two slopes. Slope from this 10, the slope becomes equals to the minus 2. The resultant slope is minus 2. So this is what the addition has to be done. So similarly also that is there for the phase angle also. So phase angle theta, which is equal to the tan inverse of minus omega tau. So in this case 0.1 omega, and the second transfer function tan inverse of minus omega. It is what the tan inverse is there. So phase angle for the one function or one system, we will consider only the tan inverse of minus 0.1 omega. So substituting omega is equal to 0, phase angle you can calculate the value of theta 1, that is nothing but the 0. So omega, when it is plus 1, the phase angle 1, this is phase angle 1, substituting the value of omega as 1, you will get the phase angle value minus 0.57. Substituting omega t, that is equals to the 10. So phase angle that comes as the minus 45. Only omega value that will be there. So similarly for the infinity, the phase angle that comes as the minus 90. Now for the second function, omega tan inverse of minus omega. So substituting omega is equal to 0, omega is equal to 1, omega is equal to 10 and omega is equal to infinity. This will not be there. So phase angle 2, that comes as the 0, 45, minus 45, minus 84 and minus 90. So overall phase angle, that is nothing but the phase angle 1 plus phase angle 2. So overall phase angle omega, which is equal to the 0, when you have to add this thing and this thing. You have to add this thing and this thing. That is what omega, which is equals to the 1, omega, which is equal to the 10. You have to add these two values, this value and this value. That is what I have done here. Similarly, for omega tends towards the infinity, this value of phase angle 1 of minus 90, that is added with this phase angle 2 value of minus 90 and has written here. So this can be also written in the tabulated form. That is omega 0, 1, 10, infinity. Then theta 1 tan inverse of minus 0.1 omega and theta 2, that is tan inverse of minus omega. So substituting all this value and adding the overall, you will get all this value. Also, you can calculate the intermittent value of 0.1 or 100 or 0.01. All these values that can also be calculated. Now here the phase angle 1 theta 1 and phase angle 2 theta 2, that will be there. So for phase angle 1, this is the theta 1, 0 to minus 90 values are there. So this is 0 to minus 90 values are there for omega tending towards from 0 to infinity. So for omega, that is 0.1, the phase angle is minus 0.571. For omega 1, the phase angle, that is minus 0.571. So this is the value of minus 0.571. And then when omega that comes as the 10, it is minus omega that comes as the 10. The phase angle value is minus 45. So this is the phase angle value of minus 45. And omega tends towards the infinity. So you will get the nearly infinite value here. Then similarly for omega theta 2, phase angle 2. However, for the phase angle omega, which is equal to the 1 value, omega which is equal to the 1 value, the phase angle 2, that is having the 45 value. So it is plotted on this point and I can connect these 2 points. And then next is omega, which is equal to the 10. The phase angle value is 84.29. So omega is equal to 10. The phase angle value is 84.29. So I can connect these 2 points here. And similarly for higher values of the infinity, it comes like this. Now it has to be added. So overall theta, that becomes equal to 0 plus 50.71. This is plus 50.71 point. For omega equals to 1. Then for omega equals to the 10, this value is minus 129.3. And then finally minus 180 for omega tends to infinity. So this is how you have to plot the phase angle and the amplitude ratio. Now we will consider the next example. So GS, that is transfer function, which is given as Kc 10s plus 1 into bracket 0.5 s plus 1. Here the tau value, that is only changing, remember that. So our first transfer function we will consider, that is Kc upon 10s plus 1. So 1 upon 10s plus 1, that will be our first transfer function. So amplitude ratio, that comes as 1 upon root of 1 plus omega tau whole square. Omega and tau. Tau is your 10. So 10 omega whole square. Now low frequency asymptote omega tends towards infinity. So I am going to substitute, low frequency asymptote omega tends towards 0. So this value becomes negligible. So amplitude ratio, that comes as the 1. So this is the equation of line passing through amplitude ratio, which is equal to the 1. So I am going to plot a straight line where amplitude ratio, that is going to be 1. Then for high frequency asymptote, I am going to have the omega tends towards the infinity. So that will depend on 10 omega. 10 omega whole square, under root of 1 plus 10 omega whole square. So 1 is negligible. So under root of 10 omega square, that means 1 upon 10 omega square omega. So this is 1 upon 10 omega. So I can take the log of this and it becomes a slope of minus 1. So slope of minus 1, that will be there. And this is the equation of line passing through amplitude ratio, which is equal to the 1 and slope of minus 1. Now to calculate the radian frequency, corner frequency. So 10 omega, that is equals to the 1. So this 10 omega, that is equals to the 1, nothing but that is equals to the 1. So omega, which is equal to the 0.1. So 0.1 is my corner frequency. So 0.1 is ऐकू येते का? ऐकू येते का?